Cody's computer. Okay. Okay, so now we're going to move on to our next section, which is 2.2. And we're going to be talking about rectangular components of a force. Okay, we're going to actually go in kind of the opposite direction. We're going to go from a force that's not on the X or Y axis, and we're going to break it into its components. Okay, so in this case, we're going to look at a force. Now, the reason we would want to put something in its X and Y components, and some of you, I'm sure, already have some of that experience in math classes and such. It's usually because we want to get the equivalent forces on an axis that we can add or subtract them more easily, kind of algebraically, if you would. So if we have forces that are at angles, and you'll notice that that capital F there, the red vector is pointing up and to the right. If we would break this into two components, that would be actually vertical on the y-axis and horizontal on the x-axis, we now can find their equivalents to have the same net effect as that one force. So we're kind of going in the opposite direction of resultants. We're going from one force and breaking it into two, but we're putting it on a convenient axis system. So again, we can then add and subtract more easily along those lines of action in the vertical and the horizontal directions. Okay. Now, what we're going to notice is we are going to give the names of the components, whatever the variable is of the force, sub X and sub Y. So here you'll see that the force itself, they just called F. So the components are Fx and Fy, respectively. The other thing that you're going to see here, and they show it correctly, is that the X and Y components are going to be acting on the axes. Do not float them out at the ends. So for instance, the Y component of the force is going to be on the Y axis. You have to show it there and label it there. But we're going to find out we can use right angle trig to calculate these lengths. And we can envision a right triangle here where that Y component is equivalent out there, but do not draw it out there because that's not where its point of action is. Okay, it needs to be at the origin where our force starts. Does that make sense to everybody? And we'll continue to reinforce that as we go along. Okay, so this is what we're going to be looking at. So rectangular components. I'm going to skip over this. If some of you may have seen the reference to I, J, and K in equations. All that is when we see I and J are your X and your Y coordinates, K would be a Z coordinate. All that is doing, instead of throwing a vector above the variable or using the greater than symbol in back of the operator, it's saying that this is a vector quantity. That's it. That's all that it's doing. So I tend not to reference the I, J, and K because, first of all, up until this book, I never saw it. Okay, I understand what they're doing, but I'm going to always call them X and Y components. So I just wanted to let you know that that's there, and you'll see the references here. So indeed, they'll write an equation instead of just saying F is equal to the quantity F, the resultant, if you would, is going to be equal to the X component plus the Y component vectorially. They now show it with that I and that J in back of it. I personally think it just adds a level of confusion. Like it's another letter, another variable that you're looking at. So I'm going to try to keep it simple. And I just want you to know that it's there. So if and when you see it along the way, it just means that that's a vector quantity. It means nothing else. Okay. All right, so let's look at concept application 2.1. We're going to do this one together. So I'm going to go underneath and you are going to find concept application 2.1. When it's not a textbook, I have my loose leaf papers in there in all different directions. Now this is going to be found on page 30 if you're following along in the e-textbook. But the concept application here, we have a force that's going up and to the left. It's force F, and it's 800 newtons is exerted on a bolt. Determine the horizontal and vertical components. Okay, so what we're going to do is we're going to draw force F going up and to the left, 800 newtons, at an angle of 35 degrees from the horizontal. Okay, so I'm going to start by calling this, and this is one of our sample, or this is one of our practice problems. So you're going to want to follow along and you're going to want to include this in what you hand in. So concept application 2.1. And I'm simply going to draw an x-axis going to the left. Here's my point A. And then a y-axis going up, because we're going to be, if you would, in the third quadrant. So this is going to be y, going to be technically negative x. And then we've got 800. I'm not going to measure it. I'm just going to use this as a straight edge. So 800 going up and to the left. And they're calling this force F. 800 newtons. 800 newtons. And then this angle right here is 35 degrees from horizontal. Okay. And they want us to break this into the X and Y components. So how we're going to do this? We're going to first draw. And again, when you do this for your homework, okay, and for this, we are just using this as a sketch. Yes, I'm using a straight edge, but I'm not scaling this. Okay. So now what you want to do is you want to draw the force first, and then you're going to draw, if you would, dotted lines or construction lines horizontally to intersect with the y-axis and vertically to intersect with the x-axis. Okay. So my arrowhead is here, 800 newtons, F. Make sure you put that label in there, label the 35. And then now on the X and Y axes, we are going to draw, I'm going to draw my vertical first. And it's going to, the tail is going to start at the origin. The tip is going to go to the intersection. And this is going to be FY. Again, on the axis. Do not float it out here. Okay, it is not located there. And then the X is going to be, the tail is going to be at the origin, and its tip is going to go to that intersection that we just created. And this is going to be FX. Okay. And now what we want to do is we want to find the vertical and the horizontal, the Y and the X components for this force. So they're going to have the same net effect as the 800 newtons would have going up and to the left at that 35 degrees. Now, what you'll notice here is because we are using the X and Y axis, we see right triangles, don't we? Okay. So if we look right here, there is a right triangle that is created. Okay. And I think actually we did components the other day, didn't we? Yeah. So this is kind of review because you guys seem to be pretty solid on that. So what we're going to do now is we see this right triangle here. And like I said, it's right here. So we're going to solve for the quantity or the magnitude of the X component using the 35 degrees and the hypotenuse, if you would. So to solve for that, okay, so this is going to be our components. Okay. So my FX is going to be equal to, this is the side adjacent to the angle that we know, and we also know the hypotenuse. So trig function, sine, cosine, tangent, which one would this be? Right. This would be the cosine, right? Yeah, because we're the side adjacent, right? So we're going to say FX is going to be equal to the cosine of 35 times the hypotenuse, which is 800 newtons, right? Does that make sense to everybody? Its formal form is the cosine of 35 is equal to FX over, it would be the 800 newtons or the hypotenuse, right? Okay, so this is kind of where that's coming from. So I'm putting FX right away and then multiplying the 800 up times the cosine. Just make sure everybody sees that. Okay. If you want to start with this step first, that's totally fine. Okay, I'm just kind of going there right away. So now if I can key in cosine 35, that'll be a decimal value times 800, 35 cosine 800 times. So we're going to get FX is equal to 655.3. 3 significant digits is fine. And then that is going to be newtons. Okay. Now, as I look here, you do not put a negative in front of the 655. The negative would only signify which direction it's going in along that x-axis. We just want the magnitude because our vector that is drawn with an arrowhead showing that it's going to the left is showing me that direction of negative. Does that make sense to everybody? Okay. If you would have the angle going from standard 0, you would get a negative value. Okay. But for as long as, and you will have not only fx, and I'm going to look at your diagram and I'm going to see the way that it's pointing, that tells me the direction. That's the only thing that the negative is for. Okay. And by showing that vector going to the left, you've got the correct direction drawn, and then we just need the magnitude. Okay. All right, let's do the y component. Okay, I'm going to do the y component right here. So my y component, even though this is showing in this direction, okay, we can envision that it's out here, right? So if we have the 35 degrees, Fy is the side opposite, and we know the hypotenuse. Now we know the leg as well, but as you know, you try to use as little calculated information as possible, right? So really our given, you want to use as much given information. We want to stick with our hypotenuse. So if we're trying to find the side opposite of an angle that's known and a hypotenuse that's known, which function, sine, cosine, or tangent? Sine, yeah. So this is going to be Fy is going to be equal to the sine of 35 times 800 newtons. Okay. And again, if you wanted to draw it in the sine 35 is equal to side opposite, which would be y over the 800 newtons, this is where that's coming from. Okay. It's just multiplying the 800 up. Okay. So if we do that, 35 sine times 800, we should get Fy is equal to 458.86, 459 would probably be good. And that would be newtons. Okay, if you add the extra decimal places, just I guard against rounding too early, because then your numbers will be significantly off otherwise. Okay, any questions? Okay. Oh, this is so fun. Oopsie, wrong way. There we go. Okay. All right, there's a concept application 2.1. Then what we're going to do is we're going to go right into concept application 2.3. This is going to be another practice problem we're going to be handing in. This one, we've got force F. It has components given. Okay. So in this case, zoom out a little bit. Fx is equal to 700 pounds. The I in back of it, all it says is it's a vector quantity. That's all that it does. So you can ignore the I as far as I'm concerned. And then our Fy is 1500, okay? So this time we're given the components and we want to find the force, okay? What that is, and then we're also going to determine its angle. Okay, so I'm going to, hopefully I should be able to fit it at the bottom here. Okay, so this is concept application 2.3. Okay. And in this case, we have the X and Y components, and we're going to find the actual force, or if you would, the resultant. So we have Y, we have a shorter X. So this is Fx is equal to 700 pounds, and Fy is equal to 1500 pounds. Proportionally, probably not quite there, but that's okay. Again, this is for illustration purposes only, so it doesn't have to be perfect. And again, I kind of like a straight edge just because I like a straight edge. You don't have to do the straight edge if you don't want. And then we want to find our F and theta. Okay. So right now, I'll give you guys a chance to write that out. How are we going to find the hypotenuse, if you would, of our right triangle? Jesse, what do you got? Oh, well, okay, we can do angle first. Do you want, oh yeah, we could do angle. Yeah. Yeah, we could use the tangent, right? We could use the tangent. So let's go ahead and solve for our theta. I think you can do either in either order. So and Jesse suggested let's use the tangent function for that, right? So because we've got this angle right here and we know the side opposite and we know the side adjacent. So tan theta is going to be the side opposite, which is going to be our 1,500 pounds. Make sure you put your units in there. Divided by 700 pounds. Pounds cancel, right? Because we're going to end up with a decimal. So then you're going to take your inverse tan of that decimal. 1,500, 700 divide. You guys end up with, I'm ending up with 64.98. Oh, 65 degrees, really, right? Yeah. We're going to be real precise. Okay, so we've got our angle. And now here too, make sure that you're showing, the work for the angle. And if you have a theta that you solved for and there's a box around it, I'm looking to your diagram to find out where is theta located. Okay, so don't just randomly put a theta. Oh, I'm going to use the tangent. I'm going to use the legs. Show me where theta is. Okay. Okay, and now we want the magnitude of F. How are we going to calculate that? We can use Pythagorean theorem. Exactly, Jesse. Yes, we have a right triangle, so we know the two legs, right? So we can say F is equal to the square root of Fy or Fx, right? You can put this in either order. So we're going to have 1,500 pounds squared plus 700 pounds squared. Units are included in here, right? Because they're going to be square units. And then when we take the square root, they'll go to normal units. So our F, what do we get? The book is getting 1655. Did you guys get that?
Yep.
Well, there you go. And now here again, you're going to notice that I have F is equal to 1655 pounds. Make sure you put your units throughout, right? And then in your final answer. And then if I'm seeing an F that you're solving for, I'm looking in your diagram. Is there an F in there? And there is, right? So make sure that you label so I know that you know what you're solving for. Okay. Isn't this fun? Aren't you looking forward to the homework? Like these are going to be fun problems, like so enjoyable. I'm excited for you guys, really. You're welcome. It is really fun. Okay. So good. So good. Let me see what we got here now. I think we're at 7:30, right? I promised you about 2 hours I talk, right? So I think we are at a good point where the next time that we meet, we're going to be doing problems where we're going to be solving for resultants using what we call the rectangular component method. So this was a good introduction to that. If we look at our homework associated with this section, the next problems that you have, for instance, 18 and 19, which are in the next blue section, okay? It says determine the X and Y components for each of the forces shown. So here is 18. There are 3 forces, and here's 19. There's 3 forces. You're not summing them and finding the resultant. You just want to find the components of each one. So you want the components of A, the components of B, the components of C, for instance. I wouldn't do them all on the same illustration. I would do part A for A, part B for B, part C for C. Does that make sense? And do individual for each one. And then this would be your origin at the middle. Brooke, you have a question. Yes, no, you wouldn't put the negatives for these because when you show, for instance, something that's going down or to the left, you're going to have, for instance, a BX going down for the B, okay? You would just show the actual value and then it's going to have a negatively directed arrowhead. That will be the sign that we use later on, okay? Yeah, you don't need to do negatives for these. Actually, I discourage it and just show them in the negative direction labeled, okay? Other questions? Virtually, do you guys have any questions? Those are those two. And then I think if I go a little bit further, you should be able to do number 22 as well. Oopsie, sorry, number 22. And then 26 is going to be the next subject that we talk about. So yeah, for those first couple. So there's about 6 problems based on where we're at right now. You should be able to do in your application problems. And again, if we go back to our application problems for module 2, and look at that PDF, you'll be able to do 2.1, 5, 7, 18, 19, and 22. So you're about at halfway point with what we've covered this evening, okay? So this evening then, I'm going to stop the recording here. And this evening, the rest of the time is for you to get a start on the homework problems. I'm going to stick around and be available to answer any questions. This time is going to be a time when you can use it as you choose. So if you choose to work independently at another time, just know that if you run into problems, then you just wouldn't have the advantage of having me around. But you always have the final answers for the problems that you have here. That way, at least when you get to the end, if you can't get that answer, then those are questions that you bring to class or try to troubleshoot, see if you can get it to work out or move on if you're good. Okay? So I am going to stop the recording at this time.